In today's lecture, we are going to talk about the symmetries of the Riemann tensor. And this is an important lecture for the reason that these guys show up all the time in general relativity work. And here I've written them all out in component form. I've written all the symmetries out in component form, which is the way you'll typically see them when you study this. We've gone to great lengths to study what the Riemann tensor is and where it came from, and we presume by now that you understand those facts. You understand about geodesic deviation. You understand about moving a vector around a closed curve and looking at its mismatch with itself when it returns to its original point. Or likewise, moving from a point to another point along two different paths, and looking at the mismatch you get when you land at the two different places going this way and this way. So you understand how the Riemann curvature probes the curvature of spacetime. Flat spacetime, you would expect no mismatch, for example. Geodesics would expect no deviation, no acceleration from one another. And zero Riemann curvature means zero curvature of flat spacetime. Oh, and you should also know how to define the Riemann curvature tensor in this mixed form, alpha, beta, gamma, delta, in terms of the connection. That is, you know this guy, right? This is using the connection on the spacetime to give you the Riemann curvature tensor. Now, I will say this, Meisner, Thorne, and Wheeler makes this point a lot. Most books don't worry about it too much, but understand that this mixed form of the Riemann curvature tensor, which is the one that we have derived in the previous lecture, we always ended up with this mixed form. And it depends entirely on the connection of the spacetime. So I use that language. I say connection on the spacetime. But watch what I mean. We're thinking that we're dealing with a four-dimensional manifold, right? A four-dimensional manifold. And a four-dimensional manifold, it's the fundamental object on this four-dimensional manifold is going to be this connection. If this manifold has geometry or has this notion of a connection, then you can define the Riemann curvature tensor. When I say connection on a space-time, I'm being a little bit heavier because I'm implying that we have a space-time. I'm not saying connection on the manifold. I'm saying we're connection on the space-time. Now, space-time is a 4D manifold, but it also has a metric, right? Whenever I talk about a space-time, I'm talking about a 4D manifold with a metric. And therefore, you have to think of these connections, the connection itself in all of its forms, the derivative of the connection here and the connection here, those things are all generative from the metric. So the metric produces the connection, and then therefore its derivative. And that's what I mean by connection on the spacetime. It presumes that floating behind the connection there is a metric when I use this word spacetime. Now, you don't have to be that way. You could talk about this mathematically and just deal with a four-dimensional manifold, in which case you may or may not have a metric behind everything. So what's interesting about this is that if you just talk about a connection without the spacetime, then this is the definition of the Riemann tensor that you're kind of stuck with, because there's no way to lower this index. Right? Lowering this index depends crucially on the existence of a metric. So when I look at the symmetries of Riemann, these two guys are very, very general and more fundamental in some sense than these guys. Because these guys will exist, these symmetries will exist just because of the connection's existence, right? Just through the definition of the Riemann tensor via its connection. These guys, in order to get to them, you need to lower this index. You have to convert this mixed Riemann tensor into a fully covariant Riemann tensor. Keeping in mind that we're now using the fully component language, right? So I say this mixed Riemann tensor. What I really mean is the components of a mixed Riemann tensor. And here I mean the components of a I guess in this case what I would write is these are the components of a 0, 4 Riemann tensor, and these are the components of a 1, 3 Riemann tensor. Those components are mixed with 1 contravariant and 3 covariant indices, and the components of this guy are not mixed. The components are fully covariant, okay? So that's what I'm literally meaning. Anyway, so I assume that you know these things. You have a good handle on what this guy means. You certainly understand this expression here, which can be used, by the way, to immediately demonstrate this, right? You can just say, okay, I'm going to swap gamma and delta. What happens? Well, if you go here and you swap, say, mu and nu, which is the equivalent, then this guy here becomes that guy. So this term becomes that term, and that term becomes that term. So that's like switching these two terms, which is around a negative sign. So the sign of those two terms switches right away. And then you look at swapping nu with eta, right? So those two terms swap, and those two terms swap. Oops, what's wrong? What's wrong? Can you tell what's wrong? What's wrong is I don't have a minus sign here, right? Right? So when you swap these two terms, this guy becomes that guy. So those two terms swap positions as well, and therefore the overall sign of this changes. So swapping those two indices changes the sign of things. And so we'll see why that can be expressed this way. So we're going to go through these one by one. This one first. Then we'll do, after we've done those two, these two will be pretty easy, and this one is kind of hard. So we'll end with that one. I don't think I'll get to this one today. This one's pretty easy too, though. All right, so let's first make sure we understand what this statement is actually saying, even if we don't have a proof of it yet. What does this actually mean? This is the component of the Riemann tensor, so I can take any component of the Riemann tensor, and it has to be able to equal itself antisymmetrized on the last two indices. So what does that exactly mean? Well, whenever I use those brackets to cover up some indices, what I'm literally saying is this is a shorthand for this expression. And this expression is antisymmetrized. So if you swap A and B, you swap these two terms and you change the sign of everything. So you're taking the average, right? You're basically taking the average of the antisymmetrized pieces together. So if I applied that to this, what would it look like? And it's not too hard to see. You just do the same thing. You ignore alpha and beta. You leave them unchanged, but you do the antisymmetry on the two indices that are indicated. And so this is what this expression means. What's important about it is now I can take this and combine it with that, right? So alpha, beta, gamma, delta is alpha, beta, gamma, delta. So I have 1/2 of this. So I can take this and move it to this side, and I'll end up with 1/2 alpha, beta, gamma, delta. This will have been moved away, equals the opposite of 1/2. And actually, let me just cross out this part. So 1/2 of this is going to equal 1/2 of its opposite, with the indices switched, which allows me to write R alpha, beta, gamma, delta equals minus R alpha, beta, delta, gamma. Now notice I haven't proven anything, right? I've just used a definition to show that this is ultimately the symmetry we're talking about. You switch the two and you switch these two indices and you change the sign. But literally the notation, you have to understand what the notation is saying. The notation literally means execute this substitution. So we still have to prove that the Riemann tensor's properties give you this symmetry, give you this symmetry here, the symmetry that we initially talked about, right? This symmetry. So we have to prove that that's true, but what it literally is mechanically telling us is this statement here. Now, fortunately, this is a very easy symmetry to demonstrate. we just begin with we're going to go into the abstract notation. I'm going to try to do as much of this in the abstract notation as I can. I think that's, this is actually an omega, by the way, because it's a form, right? And this is an omega. I guess I'll make a little thing like that. So this is our definition of the Riemann curvature tensor in abstract form. If you converted it into a coordinate basis, you would end up with components that look like that. You have it eats a covector, vector, and vector, and vector, and gives you a real number. And that's the real number it gives you. And then we had this object here, which we're pretty familiar with now, which looks like this, if I've remembered it right. And so now we just say, okay, we're interested in swapping these two indices. Well, we know that this object, these two vectors are the equivalent swap. And so if I swap x and y, I convert this guy to this guy. If I swap y and x, I convert this guy to this guy, which flips them around that minus sign. So this part changes sign. And if I swap x and y, it's a commutator, so that changes sign. So this guy changes sign. So this whole thing changes sign when I flip x and y, which ultimately means changing these two indices. And therefore, I now know that this is going to equal minus r omega w y x. And so I can immediately write down the abstract form of this, which shows that we're antisymmetric in swapping the last two arguments. And if I pushed it to the logical limit, the pedagogical limit, I can convert this into a coordinate basis, which would look like this, right? So this structure in a coordinate basis, this is the basis vector of the 1, 3 tensor product space, right? And you can see one vector and 3 basis covectors all patched together in a coordinate basis with a equivalent component. And then each of these vectors here have been broken down into their component forms. The covector here is also broken down into its component form, right? So this is what this guy looks like when you break it down into its component form. And of course, as we do with all general relativity stuff, we kind of throw all this away. It's all implied, and we just keep this guy where the ordering of these indices captures the nature of the tensor product space you're in. And now, but we do see that, I better get rid of that red. I want that red now, sorry. But we do see that these last, the reason I did this is to show these last two vectors in the argument list, they will be, they'll be basically contracted into these two basis covectors, right? And so this x and this y will end up being associated with gamma and delta. And just as a reminder, the way that works is pretty straightforward, but it ends up being that you end up with the dx gamma will operate on partial nu, and then dx delta will operate on partial mu. And then the x nu and the x mu will come out in front. So you'll end up with r alpha, beta, gamma, delta, x nu, y mu. But these two guys will give you delta functions because of the way they're constructed. This will be delta gamma eta and delta delta mu. And that will turn this gamma and eta into that'll turn this eta and mu into gamma and delta. So you'll end up with delta or gamma and delta up there. So the point I'm trying to make is that this statement here can be literally translated into a statement about these last two indices by executing these normal things we learned about in the what is a tensor part of everything, which hopefully you're very comfortable with by now. So therefore, we have now shown that in component form, we've shown this statement here through the conversion of this abstract form. We've proven this, and now that we've proven that, we write it in the typical way of expressing it is it equals R alpha beta delta, well, gamma delta. Doesn't matter what order you put those two in. Let me write that a little clearer. Gamma delta. And that is our first identity. Okay, so what about the second identity? Let's do that one. So again, we want to take a look at this thing and we want to say, well, first of all, what does it literally mean? Now we're anti-symmetrizing on 3. And as I told you before, here, we're actually taking the average of this anti-symmetrized portion. So every time you do a single flip, that counts as a negative permutation, or that is a odd permutation, and the even permutations are 2 flips. So the 2 flip ones come in with a positive sign, and the single flip ones, or the odd flip ones, come in with a negative sign. So we're going to do the same thing here. And I think this is what you get. I just kind of worked out the cycles in my head. The even cycles are easy. They're just cyclic combinations of these 3, so those will be the positive signs. And then if you just flip one, like here I flipped these 2, this one here I flipped these 2, and the last one I flipped the first and the last together, so I get the minus sign. It's 3 factorial because there's 6 of them. There's always going to be the number of anti-symmetrized, the factorial of the number, because it's every possible permutation, right? So it's the factorial of the number of indices you're permuting. So this is what this thing literally means, is that this guy adds up to 0. And what's nice is we already know one symmetry that can help us here, since we know that our alpha, beta, gamma, delta equals minus R alpha, beta, delta, gamma. It's interesting because I can take this guy and immediately flip these 2, beta and delta, to get gamma, delta, beta. And gamma, delta, beta is actually an even flip, right? This is an odd number of flips. In fact, it's 1. But if I do another flip, then it'll be an even number of flips, and it'll be back to an even thing, which is this guy. And the sign changes, so that plus becomes that minus becomes a plus. So in the presence of this identity, this fact actually simplifies quite a bit. In fact, I'll just do 2 steps here. If you flip these, change these signs, you end up with adding another, adding this together to itself, so you get this factor of 2 out in front of each of these. And then that 2 comes out and cancels with the 2 in the factorial, so you get a third, and this is the expression. So what should be pretty complicated here, because of the symmetry we've already discovered, actually shows this sort of remarkable and non-trivial expression. So we could actually write the confusing expression, beta, gamma, delta, equals, oops, I need the... this equals this guy here, this anti-symmetrized part equals this. That is easy to confuse as the definition of what this thing is, but it's not. This is the definition of this anti-symmetrized portion of the Riemann curvature tensor. But because of this existing symmetry, which is a whole special property of this guy, in this particular case, I can write this simplified expression. And again, we're just playing around with definitions, right? This here is the definition of what this means, right? I haven't proven that this is true, but I have used a unique fact already. That's the unique fact derived from the definition of what the Riemann curvature is. If this wasn't the definition of the curvature mapping, right? This curvature mapping xy, then this symmetry wouldn't be true, and I wouldn't be able to execute this simplification. So I'm using a general definition of what this antisymmetrization is, plus this one little piece to derive this fact. So this fact isn't purely mathematical. It's purely mathematical based on this idea, but it's specific to the Riemann tensor based on that idea. So we still have to prove that this is true. So how might we proceed? well, let's look at this expression. If I were to take it and operate it on three vectors, say w beta x gamma y delta, like that, then what would happen? Well, these guys would contract on these indices here, these lower indices here would contract on these indices, and I would be left with one upper index, which would be the sign of a contravariant vector left behind, right? So that could then be contracted with omega alpha, like that, and then I would end up with a number. So what this is, and I may be a little bit overdoing this point, but if I wrote it this way, this guy here is now a real number. We have to presume that I put these guys here as well. So this would be w beta x gamma y delta omega alpha. And this guy, it's a little harder to understand how these contractions would work because these guys are in brackets, but the answer is this is the definition of what that would be, right? What that would be. You go through this definition here. But what is our abstract way of writing this? Well, the abstract way of writing it is like this. This expression here represents this guy contracted into these guys. This expression here represents this guy contracted into these guys. And this expression here represents, this expression here is this guy contracted into these guys. And then, of course, there's a 1/3 out in front of all this. Now, I've done this work, I've started here, right? Which basically means I used this component notation to make the assertion that it equals 0. I use component notation to exploit the one symmetry we know about to get this in component notation. And then I took this component notation and I converted it to this abstract notation for no particularly good reason except that I prefer, first of all, I like the exercise of going between the two. I think that's part of what this lecture series is kind of about, is a lot of flexibility with notation. But mixing in one proof this notation can be a little confusing. So in principle, we could have just started from the beginning with this abstract notation. For example, we could have just written this down to begin with, right? This is the antisymmetrization of this abstract definition, where I'm just cycling these three expressions, x, y, and w. xyw, ywx, wxy, and then these are the odd flips, which get the negative sign. But the same thing will apply because we know that r is odd under the transformation of x and y. If I flop x and y for yx, this guy changes sign. So I can then take this and say, okay, I'm going to make that xy, but in order to, the price I pay is I change the sign. Well, now this term, xyw, equals this term, so I can add them together and I get my 2. So ultimately, this ends up landing in the place I just wrote down here, this place right here. And here we have it. Now, again, we used a known property of this guy. Instead of using this known property in component form, I used the known property of the curvature mapping being antisymmetric in its arguments. Okay, so now I have this guy. So I want to prove this Bianchi identity. So I want to prove that this, or I want to discover that this equals 0. So the only obvious thing to do is we have to substitute our known definition in there and see if that will get us towards the equals 0 part of this whole thing. The first thing I'll do is I'll get rid of this third, right? If I think it equals 0, that factor is not going to matter much. I mean, ultimately what's got to happen is, in order for this to have any chance of being true, this part has to equal 0, right? This factor of a third isn't going to matter. And so here's what blowing this guy up looks like when I substitute for this curvature form right here. So rxyw is this expression right here. RYWX is this expression right here, and RWXY is this expression right here. And notice I put them in, these were three separate dual space mappings, right? So I put them in one dual space mapping by linearity, right? I'm using the property that omega A plus omega B is the same as omega A plus B, right? So now I've got everything sort of wrapped up together in one sort of summation. So let's pull, so this, since this is good for arbitrary omega, now it's got to be true that this thing here is somehow always zero. Notice this is always zero, right? The theory is that if this identity is true, this Bianchi identity is true, this guy here, if this is true, it's always true. It's true for no matter how you construct the Riemann tensor out of the connection. This thing has got to be true all the time. But there's a, but I just said it's always true. But there is one important caveat, which is we're dealing with a space-time, right? And the idea of a space-time in general relativity is that it is torsion. So here are the objects that that we think add up to zero according to the supposed symmetry. And clearly for arbitrary vectors x and y, and w, there's really no reason to think that this would add up to zero. But we do know an additional piece of information. That is that we're dealing with a torsion-free environment. So I will remind you that a torsion-free space-time, this is the abstract expression for a torsion-free space-time. And we learned in our previous lecture that this ends up implying that the connection is symmetric in its bottom two indices. Right, so this is the coordinate expression for torsion-free, and this is the coordinate-free expression for a torsion-free spacetime. So you can almost see how this is going to work, right? I can definitely look at, say this guy here, the covariant derivative in the direction y of the vector w. Say I made that, well, let me write this for the sake, for these variables. So here's what that expression looks like. So I could clearly substitute for this piece, I could substitute this guy thrown on the other side, right? And so what would that end up giving me? Well, let's see, this would become a w, this would become a y, right? And then I would have to add to it plus y w, and I'm substituting for, and you'll notice everything's fine, right? I take this piece and I throw in this. Oh yeah, so I do need one other thing. I need, this isn't just yw, right? It is the covariant derivative in the direction x of yw. So I can do this again for each of them. This one here, wx, would become xw, and I think I would be adding covariant derivative in the direction y of wx. And then this last one would become, it's xy. It would become yx, and then I would add covariant derivative in the direction w of, I think it's xy. And so now it's just a matter of cancellation, right? This guy will now actually identically cancel here, and yxw will cancel identically here, and ywyx will identically cancel here, leaving us with just these terms here, right? These guys right here. So now we turn our attention to these guys. Let's take a look at this one here. this is the partial derivative in the direction x of the vector that's identified by the commutator of y and w. Now remember, this is a vector, just like w was a vector or x was a vector. This commutator is a vector. So this makes sense. This is the covariant derivative in the direction of x of the vector y comma w. As such, you can apply this torsion free rule to this guy just like you did to these guys, right? Just like we did this substitution here, we could do the same substitution there. It just looks a little funnier. But what does it actually look like? Let me write it down. So the torsion-free condition for the vector applied to the vector commutator yw and x looks like this. And this is exactly the same structure as this is. It's just that w is now a commutator of two vectors, but it's still a commutator of two vectors is a vector. So I can make this substitution for each of these. So let's do that. I'll go to a different screen. So this is what we get after the substitution. So after I substitute for this, this, and this using the torsion-free formula, this guy here, for example, is going to be expressed as, instead of the covariant derivative in the direction of the vector x of a commutator, it's going to flip, right? That's going to get substituted. I'm going to replace this with this equaling these two guys. So it's going to be the covariant derivative in the direction of the commutator of x, which remember, just a vector, and minus this new commutator, which is the commutator of x and a commutator. But it's still just a vector. So when I make that substitution, I'm going to be trading covariant derivatives in the directions of these x, y, and w with covariant derivatives in the direction of these commutators. And when I do that, I end up with these covariant derivatives in the directions of the commutators. But what's really nice is that yx cancels with ywx. This one here, this xyw cancels with this xyw, and these guys cancel identically, so they're all gone, leaving us just with this expression. But this expression is called the Jacobi identity, and it's true for any commutators, right? All commutators, the Jacobi identity, it just asserts that that's zero. You can work that out for any two objects that are being commutated. The Jacobi identity is just a mathematical identity. If you actually expand, if you do x comma yw minus wy, and then you end up with xyw minus xwy, which is what this guy expands to be, and you do it for this one and this one, and you add them all together, you're going to see it's zero 100% of the time. So that is the final proof that this expression here in totally abstract form is always equal to zero. And the caveat is torsion-free spacetime. Okay, so, and that is called the first Bianchi identity. All right, so what's the next one we have to show? We've done this one, we've done this one. So we want to now show, so now we want to work on these three that involve the completely covariant form of the Riemann tensor. So let's do that. So we begin by noticing the important fact that this curvature mapping acting on a function on the spacetime. So this is a function on the spacetime. Here, x represents all the points on spacetime. Here, x is a vector, right? Capital X and a little x. But I'll get rid of the argument for this. Maybe I should just get rid of it now to avoid confusion. But this is what that expression would be if this was acting on a regular function f. Now you can do this, right? These are covariant derivatives. You can take the covariant derivative of the function. It just so happens that that's actually equal to its partial derivative. So if we were to just quickly, the quickest way to see that that this guy is always going to be zero is to just throw it down into component notations, right? So this would immediately become x alpha f single derivative alpha, because the covariant derivative, if I did it this way, the covariant derivative of f, which is defined as f double bar alpha, right? Because it's just a function that is equal to f of alpha. That's sort of the way, that's the definition of covariant derivatives of just plain functions. If it was a covariant derivative of a vector, it would be different. You wouldn't be able to make this statement. But you can, that is the definition of a covariant derivative of a function. It's just the regular partial derivative. So that is, so let me erase this and get back to it. Whoops. So basically it's f alpha, x alpha, y beta, and then there's the two derivatives are going to act in the opposite order. It's going to be beta alpha. And then this will be x alpha, y beta, and then it'll go in the opposite order, alpha, beta, and then this piece here is going to be minus, and then this is going to be x alpha y beta f beta alpha minus x alpha y beta f alpha beta, right? And all that cancels to be 0, right? And just make sure alpha beta beta alpha, this guy cancels with this guy, and then this guy with the double negative cancels with that guy. So the important point is that the curvature mapping on any function is always 0. And the reason that's important is because now I can say that the curvature mapping, when I act on a specific function that I'm going to create out of two vectors, w and z. Now you may remember our notation for the inner product of two vectors was parentheses w comma z. That was my notation I was using for the inner product. A very standard alternative to that that's used everywhere is w dot z. That's the inner product of w and z. So w and z are both members of one vector space that has a defined inner product. Another way to think of it is as the metric tensor applied to w and z. Right? The metric tensor applied to w and z, all these three things are meant to mean identically the same thing. So I'm going to use this notation for now because that's the notation used in the book that I learned this from a long time ago. So the point is that this is a real number, right? The inner product of two vectors is a real number. So if I have two vector fields and I form this inner product, that is a function on the spacetime. So that can stand in for f, and therefore I know that this is going to equal 0 by definition. By definition, it's going to equal 0. And then on top of that, I look at this guy and I say, oh, then what is Rxy? Not that we are wondering because we've been using it so much. We should know by now. But it's a differential operation, right? It's got these covariant derivatives. And it will always obey the Leibniz rule. And this is a product that is fair to apply the Leibniz rule on. So I can now write this as w dot Rxy operating on z plus z dot Rxy operating on w equals 0. And that's always going to be true for any vector w and z and vectors x and y. And in fact, I can kind of look at this piece right here just as sort of an example and think, well, you know what? What is this guy? Well, that's a vector. This is this differential process mapping here that is working on a vector, but it's all covariant derivatives. So I know that this thing here is a vector, and this is a vector, and this represents an inner product. So this guy here, which I could think of it as G, W, R, X, Y, z if I wanted to. It's a number, right? Because that I'm thinking of as a 0-2 tensor, taking a vector. In this case, it's a capital W, not to be confused with this omega I was using back here, which is a one form. But this guy here is a number. So this is a number. So this structure is an object that takes 1, 2, 3, 4 vectors and gives me a number. So that strongly suggests that I motivate my fully covariant form of the Riemann curvature tensor, which will look an awful like the covariant form, except this slot will now have a vector, and I define it as W dot R, X, Y, Z, where the covariant, the mixed form was an omega went here, Z, X, Y, and that produced its number using a dual space mapping with omega, R, X, Y, Z. They both produce real numbers, but they both take different arguments, but they both end up producing a real number. So this is our abstract definition of the fully covariant form. Fully covariant meaning it consumes 4 vectors, right? And this guy here, as written, lives in a 0-4 tensor product space, or the tensor product space. How does it go? It goes 0-4 like that. But all that aside, that is an important point to note. That is how we're going to abstractly define this guy. But this is the true statement that's always true. It is always true that sum equals 0, and it's ultimately traceable to the fact that this is a function, and this differential operator in its particular form yields a this differential operator in this particular form always is 0. By the way, these cancellations aren't quite as trivial as I said. This cancels with this because this is a function, this is a regular partial derivative, and the order of partial derivatives don't matter. So I can convert that AB to a BA. That's why those two cancel, right? They don't just strictly cancel. They cancel because of the property of a function, a multivariable function, partial derivatives, ordinary partial derivatives of multivariable functions. They commute, and therefore those guys cancel and those guys cancel. Again, you have to flip A and B. Okay, so what's our next step in the analysis? Well, it's not very difficult, right? If this equals 0, right, and this is our definition of the fully covariant Riemann tensor, well, then this piece here, right, that is R omega Z X Y, right, or I shouldn't say omega, R W Z X Y, and that equals minus R Z W X Y, right? So by switching these two, I've introduced this minus sign. And the way that is expressed is through R alpha, beta, gamma, delta equals minus R beta, alpha, gamma, delta. And through our definition of antisymmetrization, I can say that just equals its anti-symmetrized version on the first two indices. And so that attacks the other version of this. And it all can go back to the fact that this particular curvature operation zeroes out functions, and that's what ultimately leads us to being able to show that we're antisymmetric on the first two indices. Then a very short series of steps show that if we take this mixed Riemann tensor, we can just essentially lower the index. So it is equal to the raised index of the fully component form, the fully covariant form. So this is the fully covariant form. We raise the index using the inverse metric tensor, and there's our dummy index to do it. This guy identically equals that guy. But this guy identically equals the opposite of itself with these two guys flipped, right? We know that from our first identity, right? That this mixed tensor is antisymmetric in the last two indices. So now I can write that down. But this is just the raised form of this covariant guy with the last two indices flipped. So then I look at these two must be equal. Well, if those two are equal, but that's the same as that, then I can now write R sigma beta gamma delta equals R sigma beta delta gamma. And now what I basically said is that the covariant, the fully covariant form, is antisymmetric on its last two indices. And it essentially inherits that from the mixed form. So now I've already shown just a moment ago that it's symmetric in the first two, and it's antisymmetric in the first two, and antisymmetric in the last two. And we can write that conveniently by saying R, I guess I'll go alpha, beta, gamma, delta, is R alpha, beta, gamma, delta. But what is this? So that would tend to say that it's antisymmetric, symmetrized in the first two, and is antisymmetrized in the last two. But this has a literal meaning. And let me write down that literal meaning. The first stage of the literal meaning will be, say I antisymmetrize it with respect to alpha beta first, right? If I do that first antisymmetrization, I get this. I leave these guys alone, and I break this out. It's the average of the tensor with its single flipped components. Then I antisymmetrize this and this with respect to the last two indices. And so this is literally what this means, right? I've antisymmetrized with respect to one set and with respect to another set. And that basically comes from the fact that we've inherited the antisymmetry on this from basically going through this little analysis here. And we've already shown a moment ago about how it's antisymmetric in the first two. Okay, so that takes care of the symmetry, this particular symmetry of the completely completely covariant form. So we've done this one now, when we did this one too. So this one here leaves us with this guy. This is the hardest one, and it's not that hard. First, we begin by noticing this is the first Bianchi identity, right? This is our cyclic alpha, beta, gamma, delta beta, delta, beta, gamma. This is the first Bianchi identity, which simplifies to this because of the antisymmetry in those two indices. And now we go to the front end of it, and what I would do is I will lower that index by writing G, say, mu alpha to the whole thing. And then that will leave me with, right, that will leave me with this expression, which is another way of writing R mu beta gamma delta equals 0. And I can go from here to here, right? Because if I blew this up, it wouldn't look like this, right? It would be 1 over 3 factorial, and then there would be 3 terms that are positive, and then there would be 3 terms that are negative. But again, I already know that R mu beta is antisymmetric in these last two indices. I know that symmetry already. I know that R mu beta gamma delta equals its antisymmetric part. So I know that those will combine into this form anyway. So it inherits the same antisymmetry from the mixed tensor part that we had before. So this is also a symmetry of the completely covariant Riemann tensor. And we're going to use that to show our final symmetry that we're interested in today, which is R alpha beta gamma delta equals R gamma delta alpha beta. That is, I can take these two and swap it with those two. That's not one of these typical symmetries. That's not a symmetrized or anti-symmetrized Riemann tensor. It is a different kind of symmetry. It's this sort of symmetry in pair swapping. So, but that proof isn't very difficult now that we understand this guy, because I'm going to write down this guy in all four possible forms and just add it together. So we start with, when we know that this is true. So if I put that in abstract form, I will write it this way, where W stays in position. That's that's the vector that when converted to component form will end up with the mu index. And then ZXY, XYZ, and YZX, that's the even permutations of this guy. Now, normally you would look at even in all the permutations here and anti-symmetrize, but remember, because of this, because of the unique properties or the anti-symmetry in these last two indices, it simplifies into this straight-up prescription of just adding up the even permutations. So that's with one. Now I can repeat this with Z in the lead position and then all of the even permutations after that. So if you write down that identity all four ways that are possible, you end up with this mess. And now you start looking at ways to cancel things, right? So for example, RWZXY. If I swap W and Z and add a minus sign, I'll get minus, because it's antisymmetric in the first two indices, right? We've already proven that. That's one of the other identities. I get RZWXY with a minus sign, and here's RZWXY with a plus sign. So this would cancel with this. And I can do that for most of these, but not all of them. In fact, it looks like I can get rid of 8 of them, leaving me these guys here. And what happens here is I get WXYZ and I get XWZY. So in order to make these two the same, I would have to flip this one, the W with the X. That would introduce a minus sign, but then I have to flip this one too, which introduces another minus sign. So I'm left with, let's see, R, W, X, Y, Z plus R, W, X, Y, Z, right? Okay, so what I've done is I've flipped these two, and because of the symmetry R, alpha, beta, gamma, delta, I know I get 2 minus signs. I get a minus sign for this flip and then this flip, so that's the same. So I've just doubled that down. So this is essentially, and the same is true for this, ZY, XW, YZ, XW, whoops, YZ, XW. This should be both ways, otherwise this is going to cancel, right? I'll flip those two and those two will just cancel. So what did I do wrong? Yeah, so if I was to do this, I did the cyclic thing wrong. So clearly this is RZXYW. This needs to be RZYWX, right? In order for it to be cyclic. ZYWX. And then this last one needs to be RZ WXY, and then the ZW and the WZ, these are the two that cancel, right? Like this. Those are the two that cancel. And yeah, I didn't have, these weren't even permutations. These were odd permutations. And of course, therefore, I only needed to switch one. But now I'm back in business because the ZYWX, YZXW, those combine correctly and give me R of Z, or R, let me see, R, Y, Z, wx plus r y z wx, right? So I'm basically getting two of these. That would be, and then you add up in this direction, the all equals 0. So adding all of these up equals 0. And so this ends up getting a factor of 2 and a factor of 2, which goes away. So you end up with r w x y z equals r y z w x, which is what we were trying to show. So now if I convert that into the notation of components, it becomes r alpha beta gamma delta equals r gamma delta alpha beta, right? Okay, so I think we're done. That's this guy right here. I won't prove this one, this total antisymmetry one. You don't see this one often. It shows up in Meissner, Thorne, and Wheeler, but I have never, I was actually surprised to see it there. I don't remember ever working with that one in normal work. So I'm not going to bother to show it, but it's something like all these others. You should be able to derive it from these other identities. Okay, so what have we done? We've reviewed the symmetries of the Riemann tensor. We did the symmetries of the mixed version first, and then in the presence of a metric where you can lower these indices, we see that the totally covariant form inherits the antisymmetry in the last two indices, and it also has its own antisymmetry in the first two indices, so it has that total symmetry. And so here's the first two indices symmetry. It inherits this one, and so it ends up with that. It inherits the Bianchi identity, right? So this is the first Bianchi identity, and it's also true that R alpha, beta, gamma, delta, that's also equal to 0, so that's another symmetry in there. And then there's this sort of swapping symmetry. All right, so in our next lesson, we will talk about how these symmetries of the Riemann tensor help us form other curvature tensors that are really important. The Ricci curvature tensor, the curvature scalar, the Einstein tensor needs to be explained, and the Weil tensor, and there's even something called the double dual that we'll talk about. So that'll be our next lecture. All right, see you then.